Okay, so we have a problem set come due on Wednesday and another one coming. So we'll have a couple more problem sets and then we'll start discussing the final project for the semester. All right. So last time we were talking about selection rules for absorption and emission of electromagnetic radiation by atoms, generally molecules or what have you. And selection rules are dictated by symmetries. So the selection rules for the allowed transitions are determined by the symmetries of the system. And in particular, they are dictated by parity symmetry and rotation symmetry. Those are two important symmetries that determine the allowed transitions. In addition, when one talks about selection rules, sometimes one is referring to whether a transition is just extremely weak. It's allowed, but it's just an extremely weak transition. So one calls certain transitions forbidden, even though they're not really forbidden by the symmetries, they're just extremely weak. Meaning for the same amount of intensity of the field, the transition rate will be very small. Or alternatively, if the system is excited, oh, I meant to bring my laptop. Oh well. We'll just have to sketch some things by hand. Anyway, what I was going to say is that if the atom is excited and it decays, the selection rules also determine the pathways by which it can decay, and there are dominant transitions that are affected by strong transitions versus weak transitions. So we would say that this decay path is forbidden, although it's not really forbidden, it just might be extremely weak. And that is seen in looking at, for example, the Fermi-Golden rule, which tells us about absorption of a monochromatic field oscillating at frequency omega. That transition rate depends on the square of the interaction Hamiltonian matrix element between the initial and final states. And this matrix element, well, that as we've discussed, generally we would have our interaction expressed as an expansion in the multipoles, and thus, for a given intensity of the field, the strength of that interaction depends on the size of the particular multipole matrix element. So we have an electric dipole, which is on the order of the divide in atomic units. But the magnetic dipole moment is reduced by a factor that's on the order of the fine structure constant. So the square of this matrix element will be reduced by something like the square of the fine structure constant. Now this isn't quite right what I've written here. Of course, here that this interaction depends also on 1 over the sort of the characteristic dimension, because it depends on the gradient of the field in a quadrupole transition. So that combination has the same scaling as the magnetic dipole. This is the electric quadrupole moment. So electric quadrupole, if I have a plane wave that is incident on my atom, then the strength of the interaction of electric quadrupole is on the same order. as the interaction with the magnetic dipole moment of the atom. But that is highly reduced compared to the electric dipole. Okay. The dominant effect, and what one typically thinks about as the allowed transitions, are the ones that are allowed according to the selection rules for absorption or emission via the electric dipole interaction. Okay? And so that interaction Hamiltonian then would involve the interaction between the local electric field and the dipole moment, which I might write as writing the plane wave as 1/2 of this plus its complex conjugate. Okay? So this is what we call the positive frequency component, and this is the negative frequency component. And as you remember from your studies of time-dependent perturbation theory, it's this term that has to do with absorption, and this term that has to do with emission. We'll review that again. It's not at the tip of your memory. This is a term that goes in there into the Fermi Golden Rule, and so what we need to think about is the matrix element of this observable associated with the electric dipole moment of the atom along the direction of the polarization of the field. This might be a complex polarization, it could be circular polarization, so epsilon here is a general polarization vector of a plane wave. It could be linear, elliptical, circular. And so we needed to consider this kind of matrix element in order to determine the rate of transition, and in particular what we're focusing on right now is what are the quantum numbers associated with the initial and final states that are allowed if this matrix element is not zero. Okay, so let's say what are the conditions for which this thing is not automatically zero just due to symmetry. So we just look at a component of this operator in the spherical basis. Then, according to the Wigner Eckart theorem, the good old WET, the matrix element of this component of the dipole operator takes the following form. The electric dipole moment is a vector, therefore it is a rank 1 tensor. Therefore, when expressed in terms of the Wigner Eckart theorem, we have a reduced matrix element, a reduced dipole matrix element, which depends on these quantum numbers. Here I've assumed, by the way, I'm looking for the moment at atoms with 1 electron in the valence shell. Okay, so these are the quantum numbers associated with those atoms, which I've included in this case nuclear spin. So there's generally hyperfine interaction as well. And of course, in order to apply the Wigner Eckart theorem, it was important to remember that D is a vector operator with respect to rotations generated by angular momentum. But there are many different angular momentum I could use. D is certainly a vector with respect to orbital angular momentum, because D, remember, D is nothing more than the charge of the electron times the relative coordinate of the electron relative to the nucleus. So L is the generative rotation of the bar. So that's cool. But it's also a vector with respect to J, where J is L plus S. And it's also a vector with respect to F. Where F is J plus nuclear spin. Why? Well, because the spin of the electron and the spin of the nucleus commute, are observables that commute with position, right? They act on different subsystems. If I had a tensor product of orbital spin of electron and spin of nucleus, operators that act on the different subsystems commute with orbitals. So adding in the spin doesn't change anything. And so therefore, D is a vector with respect to any of these angular momenta. They satisfy those commutation relations. And thus, here I've written it, I've used the Wigner Eckart theorem based on the fact that D is a vector with respect to F. Okay? So, and from this, what we learned, certainly immediately, we learned that delta F can be 0 plus or minus 1. Why is that? Because of the Clebsch-Gordan coefficient. I'm adding 1 unit of angular momentum, and when I add 1 unit of angular momentum to F, the F prime, according to the triangle inequality, can stay the same, or it can increase by 1 or decrease by 1, right? But of course, no F equals 0 to F equals 0. That's verboten, because there's no way I can add 1 unit of angular momentum to 0 and get back 0. And moreover, we see that delta M sub F is equal to 0 plus or minus 1, or in fact, for the particular value of Q that we have, remember Q can take on values plus 1, 0, or minus 1, because this was a rank 1 vector, a rank 1 tensor. Those are the 3 possible values of Q. And for the particular value of Q, M prime has to change in this way. All right? Moreover, we saw from parity that delta L has to be odd. However, we can say more than that because of the fact that D is a vector with respect to L. Then if I were to uncouple the basis between the spins and the orbital, I would end up with matrix elements that had the Wigner Eckart theorem there with L M sub L and L prime M sub L prime, and I have the same kind of thing for those individual matrix elements. And there too, I would have L prime and L. I know that L cannot change by more than 1. Therefore, since L cannot change by more than 1, and delta L has to be odd, we have that delta L for electric dipole transition has to change by 1. Okay. Moreover, we see the same thing, but by my same argument about uncoupling nuclear and electron, we would see delta J cannot change by more than 1 because D is a vector with respect to rotations generated by J. And for that same argument, J cannot change by more than 1. No J equals 0 to J prime equals 0. Okay. So those are the selection rules associated with an electric dipole transition. Now, as we were discussing at the end of last week, the particular transition that's driven depends on the polarization of the electric field. Okay? So if my electric field is assumed to be polarized with some polarization vector epsilon, then only the transitions that are driven depend on the components of epsilon along the direction of the particular basis vector. And this is a problem that generates a lot of confusion, I find. Because, as you notice, although K is kind of buried in here, if I wanted to place a role, remember, R here is the center of mass of the atom, so it has a role in terms of radiation pressure that we're going to talk about. The K plays no role here in terms of the direction of K, in terms of the internal relative motion of the electron relative to the nucleus. So, although the possible epsilons, of course, are restricted if it's a plane wave, right? I mean, it's transverse. What we're calling the z-axis, remember, spherical basis. We have E0 is Z, E plus and minus 1 are X plus or minus I, Y. There's some phase out front, but not really important to focus on it a moment. So, the spherical basis is space fixed. In other words, we impose a coordinate system. We decide some direction we're going to call Z. It doesn't matter. The physics can't depend on the coordinate system upon which I describe the physics, but it's convenient to put a coordinate system. So we choose one. What we call the Z-axis, the physics cannot depend on that. Now, there may be convenient choices for the Z-axis, right? I might have a strong biased magnetic field which sets a quantization axis, but in principle, the physics that happens can't depend on the direction I call the z-axis. So whether I call that z-axis the direction of propagation of the plane wave, or whether I call that z-axis the direction of a linear polarization of the light, is irrelevant. The transition rate, absorption rate, can't depend on that. So let's see how that works out. One last point. Of course, when we're calling, when we have quantum numbers like n, They are the quantum numbers that are associated with the projection of angular momentum along the chosen z-axis, whatever the z-axis is. All right? So what we say here is that if epsilon is E0, so if we've chosen, if the atom has a certain quantization axis with which we are expressing the magnetic sublevels, and if the polarization of the light is along that direction, then that polarization is E0. We call that pi light, because probably in German the P for parallel was pi. And if, on the other hand, our epsilon is either E plus or E minus, we call that perpendicular. But it's S, which was, what is perpendicular in German? It's probably something else. Exactly. So this is what we call sigma plus or sigma minus light. Okay. This is not to say, as we will see in a moment, that the light is, if it's got a sigma component to it, that it is circularly polarized. It has a circularly polarized component relative to the atomic quantization axis. Let me be clearer. Let's consider the following problem. Let's suppose I'm going to ignore the nuclear spin. So I'm going to look at a S1/2 to P3/2 transition, kind of a D2 line in an alkali. Ignoring the nuclear spin. Okay? So, we have here four magnetic sublevels associated with this excited state. These are the MJ values. And then we have 2 for the spin of the electron in the ground state. Okay? Now, which transitions are allowed here, according to electric dipole transitions? Well, first of all, the transition from here to here overall is allowed, right? Because L changes by 1. That's cool. J changes by 1. That's cool. And MJ can change by +1, -1, or 0. If the light is pi polarized, meaning it has a component which is along the direction of the axis I call the z-axis, then I drive these transitions. So pi light involves M not changing, right? Because in this case, Q equals 0. If I have sigma plus light, well, I change by 1. So this is sigma, this is pi, sigma plus, and then I have sigma minus. Okay, so those are the allowed transitions. Moreover, according to the Wigner Eckart theorem, for a given amount, the same amount of intensity, but in these different polarizations, the absorption rate will depend on the polarization. How? Well, the absorption rate is proportional to the square of the Clebsch-Gordan coefficient associated with that transition, right? Because that's what this says. So the rate of absorption for the same amount of intensity will have different relative strengths depending on the Clebsch-Gordan coefficient squared associated with the different transitions. So this Clebsch-Gordan coefficients I happen to know because they're famous, and we'll talk about them in the theory of laser cooling. This is 1, this is the square root of 2/3, this is the square root of 2/3, and this is, these are both, these diagonal guys are the square root of 1/3. Okay, so those are the Clebsch-Gordan coefficients associated with those transitions. Okay, so let's suppose I have so let's consider a linearly polarized framework. Okay? So here it is. Here's the K vector. Here's polarization vector. Now I have to decide what I'm calling the z-axis. Let's suppose that I call this the z-axis. Okay? Well, if I call this the z-axis, which transitions are driven? Sigma plus, sigma minus, or pi, or all of the above. It's all pi light. This is all pi light because all of the polarization is along the quantization axis. So I drive these transitions. And in fact, for this particular atom, the rate of transition is the same whether it's spin up or spin down. Okay. So the rate of absorption is proportional to 2/3 times the square of the reduced dipole matrix element between the initial and final state, right? But suppose that, I have the same physical situation, but suppose I chose to call this the z-axis. Okay, I might want to do that. Here's my energy level diagram again. Now I want to be, first of all, a little bit careful. When I call this plus 1/2 or minus 1/2, I mean the atom has its projection spin up or spin down along this direction. So spin up and spin down along this direction are not the same as spin up and spin down along this direction, right? I'd have to do a rotation to do that. However, in this case, it doesn't matter because the absorption rate was independent of whether it was spin up or spin down. I don't really need to worry about that because it was independent of the initial state, as long as it was linear. It's not true if it was circular because this guy is one-third less absorbing than this, right? But for linear, they're the same. It doesn't matter what the initial state. So I'm not going to worry about that part. Okay, but given this is now understood to be spin up or spin down along this direction, along the k vector, which transitions are allowed? Pi? Yes or no? No. Why not? Well, it has no component along the z-axis. Is that sigma plus or sigma minus? Or both? Both, right? Because this vector here is the x direction now, if I call this the z direction, which is equal to minus e plus e minus over root 2. So one way to say it is that linear polarization is a superposition. Let me draw this in the plane. Here's the z-axis coming out of the board. Here's x, here's y. If I have two circular polarizations going in opposite direction, as they rotate, they sweep out, as long as they have the right phase relationship between them, they sweep out a line. If I had the opposite phase, then it would oscillate along the y direction. If I had some other e to the I phi plus e to the minus I phi, it would oscillate along some diagonal direction. But equal amounts of sigma plus and sigma minus is linear. Okay, so that means that relative to this energy level diagram, where this is spin up or spin down along k, if I start here, I will drive these two transitions. In fact, what I will do is with this light, because this is a superposition of sigma plus and sigma minus, the atom will be driven into a linear superposition, a coherent superposition of these two magnetic sublevels. Now, how is that possible? Here, it went into a single magnetic sublevel, and here it's going into a superposition of magnetic sublevels. Well, that's just a change of basis. A state represented spin with some particular projection along this direction is a superposition of projections along another physical direction. So it's just a change of basis. Now, in principle, actually, this state is a superposition of this and this. So really, it's all of these guys in superposition. But the absorption rate doesn't depend on that. So I'm just going to look at one of the particular cases. All right, so this Clebsch-Gordan coefficient is 1. This Clebsch-Gordan coefficient is 1 over root 3. So the absorption rate here is what? Well, I have there are two possible paths. Half of the intensity of the light is in sigma plus. Half of the intensity of the light is in sigma minus. So I have a half of it going into Nj equals 3/2, Nj equals 1/2 squared, plus a half Nj equals minus a half d minus n s1/2 Nj equals that. So the absorption rate out of this initial state is the sum of the absorption rates associated with these two transitions. And what is that absorption rate? I'm sorry, I didn't manage my space very well here, but let me come back over here. In this case, this is equal to, well, I'm going to have the reduced matrix element factored out. Times a half the square of the first Clitoral coefficient, which is 1. That's the sigma plus part. And then the square of this Clitoral coefficient, which is the sigma minus part. So I get 4/3 over 2, which is the same, which is equal to this, as it must be. So, morals of the story here. The physics doesn't depend on what I call the z-axis. But I have to be careful about what I do choose the z-axis to be. If my axis with which I am referring to my magnetic sublevels is parallel to a linear polarization, or has a component which is parallel to the linear polarization, then the system is said to have a pi polarization component. If it has a component which is perpendicular to that axis, then it has sigma coefficients. Having sigma, driving sigma transitions doesn't mean that the light is necessarily circularly polarized. This light is linearly polarized. But relative to this axis, it's a linear combination of sigma plus and sigma minus. Now, generally speaking, unless you had some reason to choose, if you had linear polarization, unless you had some reason to choose the quantization axis in some special way, this would not be the natural choice. Why not just choose your quantization axis along this? Because that's the natural direction and I have only pi transitions. Of course, if I had a magnetic field on along this direction, it might be more natural to choose the quantization axis along the B field, and then I have sigma plus and sigma minus. Okay? Does this make sense? Constant confusion. All right. So, if our excited state and ground state different quantum numbers don't satisfy the selection rules for electric dipole transitions, it does not mean that the transition is completely forbidden. It just means that it's not allowed according to an electric dipole. So we want to now look at beyond E1. Let's continue to think about, for the moment, one electron in the valence shell. So let's think about magnetic dipole. Affectionately known as M1. So, again, our transition rate here, according to our Fermi golden rule, now is electrons, well, it might be a small nuclear effect, but that's a tiny part of this. Where again, I'm looking at, say, for example, if I had a plane wave, or not even, it doesn't have to be a plane wave, but something that's monochromatic. I mean, it could be inside a microwave cavity, or in the or the coils of some oscillating current that makes radio frequency fields. But I'm going to write this as the real part of the epsilon. Okay. My magnetic dipole operator here is the magnetic dipole associated with this one electron in the valence shell. And that is equal to minus the Bohr magneton times the orbital angular momentum plus the G factor for the electron, which is 2, times the spin of the electron. Okay. So that's the magnetic dipole operator for the one electron in the valence shell. There's a small nuclear component, but it's just tiny. It doesn't affect the forces very much. Also won't change these selection rules we're about to denote. So what can we say here? Well, this is a tensor of what rank? It's a rank 1 tensor. This is a vector. In fact, it's a vector with respect to L, S, J. All right. What about the parity? Well, remember that L is R cross P, right? So L is even under parity. S is even under parity. So what the first thing we see here, if I were to write this out, let's write out the same kind of matrix element that we had before. We have N prime, L prime, J prime, F prime. U sub Q. It's also F. according to the Wigner Eckart theorem, this is equal to so, according to these rules here, what we see, just as in an electric dipole transition, delta F prime can be 0 plus or minus 1, no F equals 0 to F prime equals 0. Delta M sub F is also, can change by 0 plus or minus 1 according to the polarization or the oscillation direction of the magnetic field by the same arguments we had for electric dipoles. That's all the same. However, we could say a few other things. Firstly, delta L. Well, again, I can do the uncoupling of the coupled basis into, in the coupled basis into uncoupled basis, uncouple the orbital from the spin. I'll have the same kind of arguments associated with the Wigner Eckart theorem now with respect to orbital, and that would tell me, according to the Clebsch-Gordan coefficients and rotational symmetry, that delta L prime is 0 plus or minus 1. However, by parity, we cannot have L change by 1. L must stay the same because of parity. So these are not allowed, and delta L must be 0. Moreover, for the magnetic interactions only act on the spin and the angular variables of the orbitals and have no effect on the radial quantum numbers. So that means that, in fact, delta N has to be 0. Which means that magnetic dipole transitions are only transitions within the fine structure multiplet. They can go between fine structure states or between hyperfine structure states within a given J. For example, let's say I have, this is the fine structure associated, I'm sorry, the hyperfine structure associated with sodium. It has different Fs and different M sub Fs. If I apply a microwave that was resonant at, whatever this is, a few gigahertz, and if the oscillation of that microwave was such that it had a component that was sigma plus, then I would drive spin changes, M sub F, combinations of nuclear and electron spins, that are M1 transitions. Okay? They are depend on the magnetic dipole moments. All right. So we have magnetic dipole. Let's look at the electric quadrupole. Well, my interaction matrix element in this case was related to the contraction summed over I and j. I use the repeated index summation. This I is the initial final. Okay? Which we could rewrite in the spherical basis in terms of the contraction between the 5 components of the irreducible tensor operator of rank 2 and some which is a complicated thing to explain, but so I'm not going to go into it exactly to figure out how you convert from the Cartesian components. You need to do a particular change of basis from these Cartesian components to these spherical components, but it can be done. The point is the following. This is the operator. That this thing depends on this. And let's again look at our matrix element. According to the Wigner Eckart theorem, this is the reduced matrix element times the Lec16 coefficient. Okay? So, first question, what are the possible changes in F? Well, this was a rank 2 tensor. And since it was a rank 2 tensor, that's why this is 2. And these Lec16 coefficients will be 0 unless F prime is related to the sum of angular momenta associated with the initial angular momentum and 2, which means F can change by nothing. It can go up or down by 1, and up or down by 2. Okay. Similarly, the delta m sub f can change by these amounts. Now, this is more complicated because the particular m sub f change, the particular q, depends on the component of this tensor in the spherical basis. So it depends not only on the direction of polarization, but the direction of change relative to that polarization. There's a quadrupole part. We'll come back to that in a moment. Again, we could do this uncoupling. We would have delta J is, because Q is a rank 2 tensor with respect to J as well. And similarly for L. What about parity? Is the electric quadrupole operator even or odd with respect to parity? How do we know? Well, what the heck is the quadrupole moment anyway? Remember, the quadrupole moment is related to the moments of the charge distribution. Where these are the coordinates of the charge. So is Q even or odd with respect to parity? It's even, because if x goes to minus x, it's quadratic. And this doesn't change. So the quadrupole tensor is even under parity. So that means delta L could be nothing or 2. But no, 0 to 0. Notice that there are transitions that are both M1 allowed and E2 allowed. The transitions which have delta L equals 0 and delta F changing by no more than 1 are both M1 and E2. And in fact, both terms contribute and both terms can interfere with one another.
Is that a problem with your microwave rates?
Generally, no, because the gradient of the field across, so remember that this depended on the strength of the magnetic field times the magnetic dipole. This depends on not only the strength of the field, but its gradient across the atom. Okay? And if we're talking about microwave, that's irrelevant, so it's not going to make an important contribution there.
So if you have a really big atom, like a Rydberg atom, then does the quadrupole transition? Do the quadrupole transitions become more important?
Again, the magnetic dipole transitions are only between states in the same in the same fine structure multiplet. So those transitions never, the quadrupoles never matter. Where it does matter, as we'll maybe see in a moment or two, is when we look at more complicated atoms with more than one electron, where the quantum numbers that I assign are not quite exact. Remember, we'll come to this in a moment, when we talked about the multi-electron atoms, we had the central field approximation, and then we had either LS coupling, Russell-Saunders, or JJ coupling, and some maybe intermediate mixing in between them. I'll come to that in a moment. Okay. Maybe that moment is now. So let's talk a little bit about before I do that, excuse me. How in the world is the angular momentum changing by 2 units? I thought this had to do with a single photon, right? This is the electric field operator that, if you maybe know from quantized electromagnetism, involves an A or an A dagger. So this is one photon. It's not a 2-photon transition. But photons carry 1 unit of angular momentum, right? So how in the world are we starting, say, in an S state and ending in a P state? Somehow the atom had to get 2 units of H bar. Where the heck is that coming from? This is 1 photon. Well, when we say the photon has 1 unit of angular momentum, what we mean is that the photon has 1 unit of spin angular momentum. The spin of the photon is spin 1. However, photons, like electrons, like neutrinos, like protons, can have orbital angular momentum as well. Now, we often don't think about the orbital angular momentum of photon, but every particle, what makes, it's not like the electron special, it has the orbital, so does photons. Photons have orbital angular momentum too. It's just that we typically don't think about it. So when I write down, let's say I have a plane wave, which we a plane wave has a definite momentum. It is an eigenstate of the momentum operator. Momentum and angular momentum do not commute. A state of definite momentum has an uncertain angular momentum. And in fact, we can decompose the eigenstates of momentum in terms of the eigenstates of orbital angular momentum. That expansion is known as the partial wave expansion, right? And so everyone hates scattering theory, but you probably saw at some point in your past life. And a plane wave can be re-expressed in terms of some which I don't remember. I remember all the variables. Let's see, do I have this stupid thing here? There it is. Yeah. So, this is just a mathematical identity which says a plane wave can be written as a superposition of partial waves. Each of the partial waves, sorry, that's Jason L. Pardon me. When I write E sub r here, this is the direction of the position vector in space, which is denoted by angles theta and phi, and this is the direction of the k vector in space, which has its own. So there are terms here which look like this. These are eigenstates of L squared and Lz. These are eigenstates of orbital angular momentum. In fact, we can think about the plane wave written this way, with the polarization and the orbital as kind of the product basis of L and S. The vector direction of the electric field is what's associated with the helicity or spin of the photons. Now, if you look in chapter 16 of Jackson, remember that one? Which has what's called vector spherical harmonics. You remember those? Vector spherical harmonics are, in fact, the coupled representation of angular momentum that couples the orbital part to the vector spin part to get total J. So when I have a plane wave, I have in there not only the possibility, I mean, this is s equals 1, and therefore, if my transition didn't depend on the gradient of the field, it was definitely just the spin part of the photon that was contributing. So electric dipoles only have to do with the spin part of the electromagnetic angular momentum. But if I start dealing with these gradients and all that, then I have to start worrying about these things, and I can't have more than one unit of angular momentum. It's coming from the orbital part of the photon.
If you had a Gaussian beam,
Yep.
would that matter a lot compared to the plane wave?
It can make a difference when, I mean, this effect here changes things. So if I have a very, very tightly focused beam where that gradient start to get, so that the gradients start to get on the order of the wavelength, because otherwise the gradient is just the wavelength, and that does affect things. But, you know, a standard old Gaussian beam, it's not going to make a difference. All right. So, now is the moment to talk about higher atoms with more than one electron. Well, really, in general, I mean, depending on the nature of the atom, how many electrons there are, how relativistic they are, we only have certain quantum numbers that are good quantum numbers, for sure. Let's say, for the moment, let's suppose we'll come back and add in the hyperfine structure in a moment. Let's think about atoms with no nuclear spin. Then the only good quantum numbers, the only perfect quantum numbers are J and M sub J. The total angular momentum of the atom is whatever it is. And then we can choose a projection, right? So all of the selection rules that we described relative to J hold for E1, M1, E2. On the other hand, we might have, if LS coupling is a good description, well then we would have quantum numbers L and S, J and MJ. Okay? So, for example, we have for the E1, we have the same kind of selection rules that we had before. No problem. Notice, of course, that can't be, so why do I have everything prime here? That in this case, the spin is the total spin associated with all of the electrons in the valence shell, which can be more than a half. And since this operator doesn't change S, we also have delta S equals 0. Okay. What about, I'm going to be bad at my Blackboard technique. You got it. M1 mu Q. Well, now remember mu is the total L plus twice the total S, sum over all the electrons. For M1, these are still true. But now delta L is 0. Actually, yeah, that's right. For a reason. An aside, parity is not -1 to the total L. What is the parity in this case? If our state of our electrons is made up of a Slater determinant with an electron configuration which has some n sub I and L sub I and m sub L sub I. These are the set of orbitals that are coupled together in my Slater determinant and then my LS coupling, as we discussed a few weeks ago. The parity is -1 L sub I product over all electrons. So each electron has a definite L. The parity associated with that orbital is -1 to the L. If I have n electrons in the valence shell, the parity is -1. However, L squared commutes with this operator. And since L squared commutes with this operator, L can't change. Moreover, S squared commutes with this operator. Therefore, S can't change. What about M2? Well, we had the same kind of thing before. Delta J is 0, plus or -1, plus or -2. Delta Mj is the same thing. Delta S, well, S commutes with the quadrupole, so delta S is 0. Delta L, in this case, can be all of these things. Why, in this case, all of these things, whereas for the single electron, we only had 0 or 2? Well, that's for this reason here. The parity is not determined by the total angular momentum. The parity is determined by the particular orbitals within that make up this total L. So well, there is a separate, an additional rule which says parity must not change. So if you remember when we looked at the periodic table some weeks ago from NIST, when we looked at the terms, sometimes you'll see the terms denoted by this with an odd or an even which denotes the parity. The parity of the term is not set by L. So, just a little sketch here. We'll come back and I'll show you something a little bit more complete. Let's look at an example. Let's say I have helium. Helium, its ground state, as we discussed, is singlet S0. There is a singlet P. This is the configuration 1s squared. The configuration 1s 2p can be split into singlet and triplet. The singlet P, this has spin 0, it's a singlet, therefore J is 1. In addition, there is a triplet P, which can have J equals 2, 1, or 0, right? Because in this case, the total spin is 1, the total orbital is 1, therefore J can be 2, 1, or 0. Somewhere around here, I don't remember where it is in helium, there is a, so this is the configuration 1s 2p, but with the triplet. There is another configuration with, out here somehow, 1s and 3d, which, for example, there is a singlet P, which splits up into, well, actually S is 0, so this is its triplet P, 2. Okay? So, which of these transitions is electric dipole allowed? Well, we can have to have delta L equals 1 for it to be a, so it can either be this or this. However, this is triplet, and this is singlet. Delta S has to be 0. So the strong transition here is this one. This one is pure E1. What about this transition? Is that E1, M1, E2, all the above?
Well, E1 is not allowed because S is not, because S is changing.
No, this is the S.
Oh,
This is 2S plus 1, so these are both.
Yeah.
So that's okay. What is delta L in this case? 2, right? So that's electric dipole. What about this transition? Well, L changes by 1. Therefore, and J changes by 1. S stays the same. Therefore, it is E1. So if I pump an atom up here, once in a while it's going to decay down here. Now, what about these guys? Are these allowed by any of these? No, they're not. Because all of these have delta S 0. So there's no way to go from triplet to singlet. However, I call you triplet, but you're not really pure triplet. There's a little bit of singlet in you. I know there is. Why is that? Because, well, that separation of triplet and singlet was only when we ignored spin-orbit coupling. The spin-orbit coupling, I mean, when we did LS coupling, we ignored that. So there's a little bit of singlet, and this is not pure triplet. When we call it triplet P, it's because it's its dominant gene, but it's got a little bit of recessive singlet. So there is some transition between those transitions are called intercombination lines. They're much weaker. Those are the kinds of lines that are being explored as, because they're very weak, they have atoms that are excited up here have very long lifetimes, therefore do not decay down very rapidly, and therefore they're good candidates for optical clocks. Okay, that said, we still have J rules. So of them, which of them, if I put a little bit of this and this, which of these transitions is E1 allowed, if it had a little bit of singlet in it? Well, I still have to have delta J changed by 0, plus 1, minus 1, or 2. I mean, no 2. No 2. So this can't go. This can go. That's, of all of the intercombination lines, that's the strongest one, because delta J is, in that case, delta J is 1. That's good. What about this one? Well, this is, again, this is a sort of, this one was kind of E1-ish, if it had a little bit of this one. This one's kind of E2-ish, because delta J is 2. What about this transition? Well, this is a J equals 0 to J equals 0. Remember, we kept saying no 0 to 0, no 0 to 0, no 0 to... This is absolutely forbidden. And the only way that this is allowed is if, to the degree to which this total J is not 0. So, for example, if I have nuclear spin, the hyperfine interaction makes this very slightly allowed. And this transition is so narrow, this is the kind of transition that's being considered for the next generation of the definition of the second. The new optical clocks, atomic clocks, will be based on the J equals 0 to J equals 0, the intercombination line. But it requires something to mix in. Nuclear spin is the easiest thing, hyperfine structure does it. But then you have problems with nuclear spin collisions, and they don't like that. So there's some other way. It's part of the ongoing research. All right. We'll end there. We got our selection rules now. And we'll take a little break and meet you in 1191 for the problems. Transitions that are affected by strong transitions versus weak transitions. So we would say that this decay path is forbidden, although it's not really forbidden, it just might be extremely weak. And that is seen in looking at, for example, the Fermi-Golden rule, which tells us about absorption of a monochromatic field oscillating at frequency omega. That transition rate depends on the square of the interaction Hamiltonian matrix element between the initial and final states. And this matrix element, well, that as we've discussed, generally we would have our interaction expressed as an expansion in the multipoles, and thus, for a given intensity of the field, the strength of that interaction depends on the size of the particular multipole matrix element. So we have an electric dipole, which is on the order of the divide in atomic units, but the magnetic dipole moment is reduced by a factor that's on the order of the fine structure constant. So the square of this matrix element will be reduced by something like the square of the fine structure constant. Now this isn't quite right what I've written here. Of course, here that this interaction depends also on 1 over the sort of the characteristic dimension, because it depends on the gradient of the field in a quadrupole transition. So that combination has the same scaling as the magnetic dipole. This is the electric quadrupole moment. So electric quadrupole, if I have a plane wave that is incident on my atom, then the strength of the interaction of electric quadrupole is on the same order. Okay, so we have a problem set due on Wednesday and another one coming. So we'll have a couple more problem sets and then we'll start discussing the final project for the semester. All right. So last time we were talking about selection rules for absorption and emission of electromagnetic radiation by atoms, generally molecules or what have you. And selection rules are dictated by symmetries. So the selection rules for the allowed transitions are determined by the symmetries of the system. And in particular, they are dictated by parity symmetry and rotation symmetry. Those are two important symmetries that determine the allowed transitions. In addition, when one talks about selection rules, sometimes one is referring to whether a transition is just extremely weak. It's allowed, but it's just an extremely weak transition. So one calls certain transitions forbidden, even though they're not really forbidden by the symmetries, they're just extremely weak. Meaning for the same amount of intensity of the field, the transition rate will be very small. Or alternatively, if the system is excited, oh, I meant to bring my laptop. Oh well. I'll just have to do a sketch some things by hand. Anyway, what I was going to say is that if the atom is excited and it decays, the selection rules also determine the pathways by which it can decay. And there are dominant trends. There are many different angular moments I could use. D is certainly a vector with respect to orbital angular momentum, because D, remember, D is nothing more than the charge of the electron times the relative coordinate of the electron relative to the nucleus. So L is the generative rotation of the bar. So that's cool. But it's also a vector with respect to J, where J is L plus S. And it's also a vector with respect to F. Where F is J plus nuclear spin. Why? Well, because the spin of the electron and the spin of the nucleus commute, are observables that commute with position, right? They act on different subsystems. I had a tensor product of orbital spin of electron and spin of nucleus, operators that act on the different subsystems commute with orbitals. So adding in the spin doesn't change anything. And so therefore, D is a vector with respect to any of these angular momenta. They satisfy those commutation relations. And thus, here I've written it, I've used the Wigner Eckart theorem based on the fact that D is a vector with respect to F. Okay? So, and from this, what we learned, certainly immediately, we learned that as the interaction with the magnetic dipole moment of the atom, that is highly reduced compared to the electric dipole. Okay? The dominant effect, and what one typically thinks about as the allowed transitions, are the ones that are allowed according to the selection rules for absorption or emission via the electric dipole interaction. Okay? And so that interaction Hamiltonian then would involve the interaction between the local electric field and the dipole moment, which I might write as writing the plane wave as 1/2 of this plus its complex conjugate. Okay? So this is what we call the positive frequency component, and this is the negative frequency component. And as you remember from your studies of time-dependent perturbation theory, it's this term that has to do with absorption, and this term that has to do with emission. We'll review that again. It's not at the tip of your memory. This is a term that goes in there into the Fermi golden rule, and so what we need to think about is the matrix element of this observable associated with the electric dipole moment of the atom along the direction of the polarization of the field. This might be a complex polarization, it could be circular polarization. So epsilon here is a general polarization vector of a plane wave. It could be linear, elliptical, circular. And so we needed to consider this kind of matrix element in order to determine the rate of transition. And in particular, what we're focusing on right now is what are the quantum numbers associated with the initial and final states that are allowed if this matrix element is not zero. Okay, so they say, what are the conditions for which this thing is not automatically zero, just due to symmetry? So we just look at a component of this operator in the spherical basis. Then, according to the Wigner Eckart theorem, the good old WET, the matrix element of this component of the dipole operator takes the following form. The electric dipole moment is a vector, therefore it is a rank 1 tensor. Therefore, when expressed in terms of the Wigner Eckart theorem, we have a reduced matrix element, a reduced dipole matrix element, which depends on these quantum numbers. Here I've assumed, by the way, I'm looking for the moment at atoms with one electron in the valence shell. Okay, so these are the quantum numbers associated with those atoms, which which I've included in this case nuclear spin. So there's generally hyperfine interaction as well. And of course, in order to apply the Wigner Eckart theorem, it was important to remember that D is a vector operator with respect to rotations generated by angular momentum. But that is, there